Hello, everyone. Our project is AI models as pseudo-random generators. Basically, we wanted to see if AI models like ChatGPT or Cadastral could actually make random-looking numbers sequences. Sounds simple, but randomness is such a huge deal in security, so we wanted to test how good they really are. What we're looking at here is whether AI can make high-entropy, unpredictable sequences, and this matters because encryption keys rely on this randomness. If an AI secretly repeats patterns, it makes it easier for someone to crack. So the main question was, can these models actually act like real random number generators or not? We tested a few different models, two versions of Cadastral, ChatGPT 5.1, ChatGPT 4.0, and an online random number generator as our control. Each AI model has different training goals, so comparing them helps us to see which ones behave more random than others. To keep things fair, we gave every model the same strict prompt. Give us 2048 digits with no patterns, no text, just digits. This forced the models to improvise randomness without hiding behind normal text. And it's a good way to expose whether the model naturally falls into patterns or actually just mixes things up.
All right, so before we talk about AI randomness, we need to understand the difference between true random generators and pseudo-random generators. A TRNG or true random number generator gets its randomness from physical processes, things like atmospheric noise or quantum behavior. This is because these sources are naturally unpredictable. The output can't be reproduced or predicted. A PRNG, on the other hand, is completely algorithmic. It starts from a seed value and generates a sequence that looks random, quote unquote, but it's actually deterministic. If you know the seed, you can recreate the entire sequence. Large language models fall into this category. They may look creative or unpredictable, but if you give them the same inputs, they're ultimately deterministic, and that's why they behave more like PRNGs than true random sources. When we test whether something is random, we look at a few statistical properties. The first is entropy. This is basically a measure of unpredictability. The higher the entropy means, each bit is harder to guess and doesn't depend on the previous bits. Then we look at p-values. This tells us whether a sequence behaves like something that came from truly a random source. If a p-value is extremely low, then that means the sequence is unlikely to be random. It starts to show patterns or structures. And the big point here is that any bias or predictable pattern becomes a security risk. If an attacker, for example, can find structures in what's supposed to be random, they can start predicting future outputs. So these tests are critical when evaluating whether an AI model can safely behave like a random generator. To evaluate the randomness of our sequences, we use tests that are industry standard for checking PRNG quality. We run tests like the monobit test, which checks whether zeros and ones are balanced, and the runs test, which measures how often the sequence switches between them. We also run block frequency to see if randomness is evenly distributed in smaller sections. And we check the approximate entropy, which looks for repeated patterns. If a generator passes these tests, it means the output behaves statistically like true random data. These are the same tests used to validate cryptographic RNGs, so they give us a strong benchmark when comparing AI models against the real randomness.
Okay, so today I'm going to be going over the 5 different tests that we do in order to measure randomness within the bit stream we generate. So the first test we have is monobit frequency. This is essentially checking to make sure there's an equal proportion of zeros to ones in the sequence that we generate. Excuse me. The goal is roughly 50% zeros to 50% ones, ensuring that there's zero skew of too many zeros or too many ones in relation to the other digit. Because if there is a skew or a bias, that means that the sequence is predictable and not truly random. So you want roughly a 50% output. And in our failure condition here, if 70% output occurs, that means that it's skewed 70% to one digit, indicating that it's not truly random. So our second test we do is called the runs test. This is a run is a sequence of identical bits, and this test essentially measures how often the sequence is going to switch between 0 and 1. If it switches too few times, it's considered clumpy, indicated by our example here, 4 zeros followed by 4 ones. That itself is predictable. However, there can be too many switches, meaning that it's alternating perfectly between 0 and 1, which is also completely predictable. So the goal in the runs test is a truly random and unpredictable amount of switching between digits, not following any sort of pattern on either side. So for test 3, this is called block frequency. This test basically divides the bit stream we generate into fixed size blocks and checks how balanced each section or each block is. Random data should have uniform distributions of zeros and ones within every block. However, inconsistent or not truly random or uneven block distributions indicate there's some sort of pattern or structure within the block, or in general. So, in the results of our tests, the Codestral models, both of them ended up failing. Some of the block sections were very dense with ones, while others were completely empty. And in ChatGPT 4.0 actually passed this test. The randomness was evenly distributed throughout the entire sequence and within every block that was tested. So for the fourth test, this is the entropy test, or otherwise known as Shannon entropy. This basically looks like this test looks to quantify the unpredictability in our bit stream. Essentially, the results of this test, any value that nears 1.0 indicates a very high level of randomness or entropy, and values that near 0.0 indicate a very low level of randomness, often redundant or any other sort of repeated pattern in the bit stream. So actually all LLM models that we tested passed the Shannon entropy test with at least a 0.95 or higher, indicating that there's a high amount of variability. However, none of the models we tested actually met 1.0 itself, indicating that they're not truly random. There is some sort of pattern there, albeit very minuscule. Now for the final test we had is the compression ratio. Essentially, all the compression ratio is assessing how well the bit stream we generate can be compressed. Truly random sequences cannot be compressed significantly because they lack any sort of pattern within the bit stream. So a low compression ratio indicates that it's has a high compressibility rate, meaning the data contains some sort of repeating structure and is not random. However, a high compression ratio indicates that it's very hard to compress, meaning the data is closer to random and does not have repeating structures.
Okay, so now I'm going to take you through the Python script that we use to test each model. The first thing we did in the Python script was convert the model output, the digits, to a bit string. This takes the model's raw text output using the digits 0 through 9 and converts each digit into its 4-bit binary representation, and then takes those binaries and puts them into one long string of characters with no spaces. Okay, this second section is where we did the NIST-style statistical tests on the bit string. So the first test that we did was a monobit frequency test. This checks whether the number of ones and zeros in the bit stream is close to a 50-50 split. It returns a p-value, and the higher the p-value, the better. Okay, the next test we did was the runs test. This counts how many times the bit value changes from 0 to 1 or 1 to 0 and compares this to what is expected for random data. It also returns a p-value, the higher the better. However, for this test, we do not do a hard fail on bias. Instead, we always compute a p-value so that we can compare how bad the different sequences are, since we know that these are all pseudo-random and they're not going to be random. Okay, the next test we run is the block frequency test. The block frequency test splits the bit stream into blocks of size m and checks whether each block has about 50% ones. This uses a chi-square statistic and the incomplete gamma function to compute a p-value. The next test after that is to compute the Shannon entropy of the bit stream. This measures how unpredictable the bits are. Value is between 0 and 1. 1 is ideal for random bits. And the final test that we ran here is the compression ratio. This is to compute how well the bit stream can be compressed using gzip. This returns compressed size and original size. Random data should not be able to compress that much. The ratio should be close to 1. And a very small ratio means that the data has strong patterns and compresses very well, which means it's really far from random. Okay, so section 3 of this script is the helper functions, which converts the raw metrics to scores between 0 to 1. So for the first one, it converts a p-value to a score between 0 and 1. So a p-value around 5 is good randomness, so that'll give you a score near 1. A p-value near 0 or near 1 is bad, and that'll give you a score near 0. This lets us compare tests on the same scale. So these all pretty much just do the same thing, but for each different test. All right, and then the fourth section is the main driver. This runs all the tests on the model output. And then down here at the bottom, I'll give you an example of how this works. So right here, I pasted in the raw output from the GPT 5.1 model. And then when I run it, it'll give us all of our tests and all the scores that it calculated. And then finally down here, this randomness index is the average of all the scores. So this is the main thing that we could use to compare each model and rank them.
Now let's look at how the specific models performed, starting with the code straw models. Unfortunately, both code straw models 25.01 and 2 failed to generate true randomness. They exhibited significant structural bias with a compression ratio of 1.3%. This means generated numbers were so repetitive that they could be massively compressed. Statistically, their p-values were near 0, making it impossible for these sequences to be considered truly random. We believe this happened because code straw is optimized for coding, which requires strict syntax and lots of repetition, which may make the language model stiffer than other language models. And we did record about a 25% skew, meaning there were significantly more ones or zeros. In comparison to the 4.0 and 5.1 models for GPT, the GPT models perform significantly better, showing almost a 10 times improvement in compression resistance compared to the code straw. Statistically tying with our group control, the online random generator, in terms of compressibility. However, they weren't perfect, but they looked way more random, and they still failed the NIST, just like the code straw did, but with a similar 25% imbalance, but it did perform better overall.
This slide displays the metrics of all of the tests we performed on each language model. The gray section is the online random number generator, which is our control group. So for our bit imbalance, it's a consistent 25% bias, meaning that each model has a favorite digit. And then the most dramatic column is the compression ratio, which has the largest difference between our Codestral and ChatGPT models. The ChatGPT models maintain a healthy 16%, while the Codestrals collapse to the 1%. It is the mathematical equivalent of a flat line, which proved its output was 99% predictable structure rather than noise. And then interestingly, the Shannon entropy score of 0.95 was kind of across the board. Just kind of shows that all the AI can mimic the appearance of complexity without actually having the substance of randomness. And then for the runs, p-value, as you can see, all these numbers are very small, and they all failed. So to actually pass this test, this value has to be past the threshold of 0.01, meaning that all of these can stimulate randomness, but a computer can still mathematically distinguish it from true randomness. So even though ChatGPT 4.0 did well in all the other metrics, it still is not actually true randomness. And then for the randomness index, this is kind of just a culmination of all the other statistics. As you can see, ChatGPT 4.0 has the same value as the online random number generator. And then there's a little bit of a drop, but the small drop in numbers is actually very significant. Shows that this model is actually much less, it is much worse at having a pseudo-random number generation, and then both the Codestral models are significantly worse at pseudo-random number generation. So, kind of in conclusion, no model achieved true randomness. ChatGPT 4.0 is the functional winner. It produces pseudo-random sequences that are statistically comparable to a standard algorithm for general tasks, Then the codestral models exhibited significant structural bias, and then high compressibility, which makes them unsuitable for PRNG applications.